Thank you, Chair, for the introduction. And I'm Dr. Antonio Pallotti, Research Supervisor in Technoscience and Head of the Computational Graphology Laboratory at the University of Rome San Raffaele. The work that I will show you, as in the title, is a company internship collaboration under my supervision, Prof. Matteo Antonio Russo of the Medical Bioimaging Center of the San Raffaele Research Hospital of Rome, and Dr. Arianna Mencattini in the Department of Electronic Engineering, Università Roma Tor Vergata. I leave the floor to the two trainees, Tiziana Tocci and Emanuele Angelo Antonio, the latter currently Technoscience Industrial PhD student at the University of Rome for Italico.
Good afternoon, everyone. Thank you for the presentation. And so we'll start with a brief introduction in which we will talk about the context in which the project develops and say something about naturally the project goals. So biomedical digital images are at the heart of medical science, fundamental in diagnostic processes and in understanding the anatomy and the physiology of the human body. Biomedical pictures can photograph entire body regions, entire organs, or only a tissue or few cells, as in the case of histological examinations. Working on digital biomedical images allows to develop and apply image processing techniques in order to develop some diagnostic support tools for the physicians. So the context in which the work develops is the context of telemedicine, and in particular of the telepathology. Telepathology is a branch of telemedicine, and this is defined as the practice of remote pathology, which uses technologies and telecommunications for the transmission of digital images. In this project, we are dealing with a particular disease, a rare disease that is the Fabry disease, that is a X-linked lysosomal storage disease caused by an alpha-galactosidase A deficiency or mutation. And this enzyme is responsible for the hydrolysis of glycolipids and lipids, and so the disease causes intracellular accumulation of glycosphingolipids in phagolysosomes, also known and called glycolipid bodies. This disease is quite rare, with a reported incidence of one patient over 100,000, but these numbers can underestimate the presence of the disease. In the last years, the enzyme replacement therapies allow to have a crop of the disease developments, but these kind of therapies are very expensive, and we are talking about $150,000 per year per each patient, so a very high cost. The symptoms of the disease are pain in hands and feet, angiokeratomas, corneal opacities, and hearing loss. And so the disease has a very important impact on the quality of life of those affected. And the disease follows with multisystemic progressive problems as renal insufficiency, cardiomyopathy, arrhythmias, and recurrent strokes. In order to obtain good results with the therapies, it's very important to diagnose the disease in an initial stage. But the normal diagnostic tools are not able to detect the disease in a preclinical step or in an initial stage. So at the moment, histological tests of cellular tissue samples were performed with a manual image analysis done by technical personnel with an only qualitative evaluation of the images and a very big expenditure of time. So the aim of the study is to develop fast algorithms to automatically detect and quantify the glycolipid bodies inside the cellular tissue, and more in general, another goal is to make the algorithms available for the in mobile devices with a view to the telepathology and the telelaboratory. So this work was carried out on 20 histological images of myocardium, made available by the MEBI called IRIX San Raffaele Roma, acquired with the Nikon Eclipse microscope and using the NIS element software. The dataset of 20 histological RGB images is composed by 8 images in 20 ver and 12 images in 40 ver, and so we can observe in this slide, why it's too small, but the images have two different magnifications. The image processing software used are MATLAB, and in particular the image processing toolbox of MATLAB, and also the MATLAB mobile application, that is the application released by MathWorks for running MATLAB in the mobile devices. At the end, the last image processing software is the ImageA software, a Java-based software entirely dedicated to the image processing and developed by the National Institute of Health. Two slightly different algorithms were implemented in order to segment the cellular tissue and then the glycolipid bodies. The first algorithm that I called image segmenter app-based algorithm used the image segmenter applicative for the development of a particular function used for the glycolipid bodies detection. So the code begins with the image filtering using an anisotropic diffusion filter in order to increase the color contrast of the image. After that, the code follows with the cellular segmentation done using the OTSU method. This method is a thresholding segmentation method that splits the pixel into two different classes, comparing them with a threshold value opportunely chosen. So it is an automatic histogram thresholding method for digital images based on the color contrast between the cellular tissue and the background of the image. After that, the MATLAB function region props of the image segmenter toolbox were used in order to link the pixel, the white pixels of the cellular tissue together, so to form objects that in the images are the cells, in order to calculate the area occupied by the cellular tissue in the examining image. At the end, the code follows with the glycolipid bodies detection using, in this case, the image segmenter applicative for the circular Oath transform, with the aim of detecting circular objects inside the image. Naturally, some morphological operations was done in order to refine the mask, in particular regarding the glycolipid bodies mask, due to the fact that naturally the accumulation structures have not precisely circle shapes, but have a particular shape also if very difficult to detect. At the end, the algorithm extracts some different parameters as the number of glycolipid bodies, the overall area of glycolipid bodies and both of cellular tissue, and the ratio between the areas. The second proposed algorithm is entirely based on the OTSU thresholding method, and it starts with an image preprocessing process composed by an image analysis in the color space of YCBCR. So the image is converted into the YCBCR channel that splits the image in three different channels, so the luminance Y, the chroma blue and chroma red channels. How it is possible to observe in the figure, in our case, the Y channel showed the best contrast, and so this channel has been chosen for the rest of the processing. Other techniques have been used for increase the contrast. The algorithm follows with the segmentation of the cellular structures performed using the multi-level OTSU thresholding algorithm, and in particular using a 7-threshold OTSU method, followed naturally with some morphological operations. But before, during the multi-level OTSU thresholding method, a 3-level Gaussian pyramid reduction was done in order to reduce the resolution of the image. it is very important because during the detection of the cells, we are focused on the edges of the cellular tissue. So we don't want to see two details inside the image. But naturally, after the cellular segmentation, a three-level Gaussian pyramid expansion was done in order to recover the resolution lost. At the end, the glycolipid body segmentation was done also in this case using the multi-level also thresholding method without the Gaussian pyramid reduction, because in this case we want to highlight the details of the images and so the glycolipid bodies. Two slender and lighter versions of both the algorithms were developed in order to implement them on mobile devices. In particular, the device used is a smartphone, an Android smartphone, the Ricoh Y81 with Android 10, in which the easy start. The most important steps of the algorithms remain unchanged naturally, while the parts regarding the displaying and saving of outputs and images was simplified. Here in this slide we can observe three different screenshots of the MATLAB application, and it is important to say that the user have not to modify the code, but it only have to play the code, so run the code, and then the code follow analyzing all the images inside the database. So let's see some results. The results obtained with the developed tools are promising. In all the versions of the algorithms. In particular, good results were obtained in terms of execution time in comparison with the time expended for the manual analysis. In this slide, the table above show the comparison between the glycolipid bodies counted with the manual analysis without a dedicated software and the automatic analysis. This is a sort of pilot study, pilot result, because in the manual analysis performed by the technical personnel of MEBIC, these parameters, so the number of glycolipids, is not yet extracted. While in the second table we can observe the a very important result that are the execution times of the codes. In particular, we can observe that the manual MEBIC analysis need 3 hours for the process of 16 images, while other our algorithms are very more fast. For example, the image segmenter tool need 9 minutes per image, but 2 hours and 20 minutes for process 20 images and not 16. But the most important result, in my opinion, is that the mobile applicative allow to have an image analysis in really few seconds, exploiting naturally the cloud computing. Comparing the area ratio parameter, we can see that the graph in this slide shows some interesting results. We can observe that the results obtained are aligned in both the software and naturally aligned with the manual analysis. But an important thing to say is that the manual analysis is affected by operator-dependent variability that is very difficult to quantify. And also I want to highlight the fact that our algorithms are able to process 20 images, while the manual analysis software only 16 images due to 4 images with very low contrast. So in conclusion, we can assess that the proposed algorithms allow to automatically analyze histological microscopic images, identifying cells and glycolipid bodies, counting them and computing the occupied area. The developed tools show a very low running times, and so a very great time saving in all the versions of the algorithms, and also in the mobile versions that are very performing, exploiting the cloud computing power of the MATLAB cloud. Thanks to it, the algorithms in the mobile versions have very great portability, allowing to make the images analysis available to the physician in any place, simply using a smartphone or a tablet with an internet connection, constituting a powerful tool for the Fabry disease automatic recognition in telepathology. At the end, the future develops of this work. The future developments of this work are many, naturally. First of all, the test of the algorithms on a larger number of the images, and also the test of other segmentation techniques, mostly to improve the performance of the algorithms with the low contrast images that are a very difficult situation for the normal segmentation techniques. So we can try to use the artificial neural networks, exploiting the potential of deep learning image segmentation, but naturally, in order to do that, it is crucial to have a dataset expansion using much more images, also with different staining and different dyes. At the end, the other future developments regard naturally in the field of the teleconsultation and telepathology, with the broader goal of portable embroidery, with performing tools usable directly on the mobile devices and directly usable by the physicians. And that's it. Thank you for your attention, and I want to thank naturally all the team that collaborate in this project.